order for us to graph an exponential function, we want to be able to analyze a few attributes. Recall that there's a connection between this number here and our y-intercept. So in this case, 2 is our y-intercept. But why does that happen? Remember that for our y-intercept, x is always 0. So what would this look like? What would this problem look like if we replaced this x with 0? Well, the problem would then become 2 times 3 to the 0 power. If you remember from Algebra 1, 3 to the 0 power is not 0. 3 to the 0 power means 1. So this problem is really 2 times 1. 2 times 1 is 2. If you wanted a quick reason why 3 to the 0 power or any number to the 0 power is 1, remember that if we have 3 to the 1 divided by 3 to the 1, that we would subtract the powers, and this is the same as 3 to the 0. Or in other words, if we had 5 to the 1 over 5 to the 1, this is the same as 5 to the 1 minus 1, which is 0. Notice that we're dividing a number by the same number. So what's 3 divided by 3? It's going to be 1. What's 5 divided by 5? That's going to be 1 also. So any number to the 0 power is 1. Let's apply this information to find the intercept of the given problem. Remember that for the y-intercept, x is always 0. So we're going to replace our x value with 0. So in this case, our problem would look like 2 times 3 to the 0 plus 1. 3 to the 0, we remember, is really 1. So this is 2 times 1 plus 1. 2 times 1 is 2. So now we have 2 plus 1. And 2 plus 1 is 3. So our y-intercept is 3. So our y-intercept here is going to be 0, 3. But what can we say about whether this function is increasing or decreasing? From the previous examples that we did, we would look at this number here to determine if its absolute value is greater than 1. So remember, the absolute value of 3 is equal to 3. And 3 is greater than 1. Whenever this happens, we know that our graph is going to increase. Whenever this number ends up being greater than 1, we know it's going to increase. And so in this case, talking about whether it's increasing or decreasing, we know that it's going to be increasing. One thing that we want to note as well is that the parent function, if we started with y equals 2 times 3 to the x, this has 0 as a horizontal asymptote. In other words, our function would get closer and closer to 0, but would never actually touch 0. The reason why this happens is because there's no way that we can put a number here for x and end up with 0 here as an answer. So we can get closer and closer. If we choose negative numbers, we're going to end up with smaller and smaller fractional values, but this number will never equal 0. So since y won't equal 0, this particular function would have an asymptote at y equals 0. But look at what happens here. We're saying plus 1. So in other words, we're moving everything up 1. So our asymptote will be at y equals 1. A quick way of figuring out the asymptote is that whatever we're adding or subtracting will always be our horizontal asymptote. But what about the range? If we notice here that we will never have y values down here. All of our y values are from the asymptote up. So what that tells us in this case, since our asymptote is at 1, our range would have to be from 1 to infinity. And if we look at our domain, whether we go to the left or we go to the right, we will always have an x value that we can input. In other words, we can put any number that we want to for a power and it will be okay. So our domain would be from negative infinity to positive infinity. For this particular function, one thing that we notice is that right here, what we're raising to the power of x, in other words, our base, this time is its absolute value, which is 1/3, that number is greater than 0, but less than 1. Whenever this happens, our graph will always look like it's decreasing or decaying. So in terms of whether our function is increasing or decreasing, this one is decreasing. And that has to do with the 1/3. Well, what about the other attributes? We already know from the previous example that if we want to look at the asymptote, this is where we'll need to look. So our asymptote here will be y equals -3. What about our intercept? Remember, our our y-intercept will happen whenever x is equal to 0. So if we substituted 0 here for x, what exactly would happen? Well, our problem would look like 4 times 1/3 to the 0 power minus 3. 1/3 to the 0 power is 1. So that's 4 times 1 minus 3. 4 times 1 is 4, and we're subtracting 3, so that's going to give us 1. So that means that our intercept is going to be at 0, 1. What about our range? Remember that our range is connected with our asymptote. So whatever our asymptote is, that represents the lowest value that it's going to approach. So our range is from -3 to positive infinity. And just as before, for all exponential functions, our domain will go from negative infinity to positive infinity. Suppose we're asked the question, to what power would we raise 10 to get 1? Well, from what we discussed before, 1 is the same as 10 to the 0 power. So the question that we asked could also have been written log base 10. Notice that our base here is 10 of 1 equals what number? So we know that log base 10 of 1 equals 0, because again, 10 to the 0 power is 1. And remember, logs are powers. Well, what about if we ask the question, to what power would you raise 10 to get 1/10? Well, 1/10 is the same as 10 to the -1. So what we're asking is, to what power would we raise 10, or log base 10 of 1/10, and we know that that's going to give us a negative value. So we can keep going and ask this question, log base 10 of 1 over 100, and that's really 10 to the -2nd power, so it will be -2. If you notice, for our log functions, we can end up with negative values, but every number that we put in has to be positive. So in other words, the domain of a log function will always be from whatever makes our argument positive, in this case, 0 to infinity. If we shifted our log function left or right, this value might change. But the overall idea is that what we put here, what we end up with as our argument for our log function, has to be a positive number. We also know that for our range, just as we had in the example here, we can have negative numbers. We can also clearly have positive numbers. So our range would be from negative infinity to positive infinity. This will always happen for every log function. For log functions, the domain will always be from what makes the input positive all the way to infinity as well. In order for us to graph this particular log function, there's something else that we need to know as well, or remember. And that is that if we have, as an example, 2 to the x, and we have, remember, the base here is 2. So if we have log base 2 of x and we compose these, that the composition will always give us x. And this is because these functions are inverses of each other. So if I do, as an example, 2 to the log base 2 of x, that this is going to equal x. Or if I do 2 to the log base 2 of x, then this is still going to be x. So I can use that to my advantage. So suppose that I want to find the x-intercept, which means that our function has to equal 0. This would be something useful for us to get rid of the log part of our expression. So in other words, if I make the base 6, so I say this left side is 6 to the 0 power, and I make the base 6 on the right side also. In other words, I'm saying on the right side, this side here, that I'm doing the base is 6, and I'm doing log base 6 of 4x minus 3. Remember that this and this, they're going to cancel each other out, just like we had with 2 to the log base 2 of x, that these two cancel each other out and just left us with x. So in this case, the log base 6 and the base of 6 cancel each other out, and over on the right hand side, we just have 4x minus 3. Remember that 6 to the 0 power is 1. So we can solve for x by adding 3 to both sides. So we add 3 to both sides of our equation. We end up with 4x equals 4. Divide both sides by 4, and we end up with x equals 1. So our intercept here, our x-intercept, is going to be 1, 0. In terms of our domain and range, well, that part is easy because remember that the domain of log functions are always going to go from negative infinity to positive infinity. The domain, remember, the domain is going to require that whatever we input for the log, whatever goes here, has to be greater than 0. It has to be a positive number. So we're going to say 4x minus 3 has to be greater than 0. So we add 3 to both sides of our inequality. And so 4x is greater than 3. We divide both sides by 4. And so x is greater than 3/4. If we want to write this with interval notation, what we're saying is that here's 3/4, and we have all the x values greater than that, even going to positive infinity. So this right here represents x greater than 3/4. So in interval notation, what we're saying is that we're saying everything to the right of 3/4 is something that we can use. So the domain would be from 3/4 to infinity. Remember that this particular value means that we will not have anything on our graph, any x value, that's going to be on this side of 3/4. Everything is going to be on that side of 3/4. So what that means for us is that we're going to have a vertical asymptote at 3/4. And our values would end up getting closer and closer to 3/4, but it would never touch. So our asymptote here is this 3/4. So we're going to say x equals 3/4 is our vertical asymptote. In terms of this function from our sketch, we can see that it's going to be increasing. So our function is increasing. So suppose that we wanted to find the intercept of this function. The y-intercept, the x-intercept of this function. That means that for the x-intercept, remember that y has to equal 0. In other words, our function is equal to 0. So we're asking, when is the log base 5 of 3x plus 2 going to equal 0? Remember that we said that we could raise each side to whatever the base is. Remember, the base is 5 here. So the log base 5 and the 5 are going to cancel each other out. And that leaves us with, on the right-hand side, just 3x plus 2. 5 to the 0 is 1, and we can keep working this out algebraically to get x by itself. So 3x is going to equal negative 1. Divide both sides by 3, and so x equals negative 1/3. In other words, our intercept, our x-intercept, is going to be negative 1/3, comma 0. Now let's try to find our other attributes. The range is easy. The range will always go from negative infinity to positive infinity for every log function. The domain is going to be anything that's going to make this argument for our log function positive. So we have to figure out when 3x plus 2 will be greater than 0. We subtract 2 from both sides to get x by itself. So 3x has to be greater than negative 2. If we divide both sides by 3, we end up with that x has to be greater than negative 2/3. So in other words, our domain is from negative 2/3 to infinity, and our asymptote will be where x is equal to negative 2/3.